It's a great pleasure for me to welcome you to this special colloquium inserted in the webinar series of the graduate program in physics of the Federal University of Pará in Amazonia, Brazil. I ask everyone to kindly leave the microphone and camera turned off, except for the moment you're going to speak. Questions will be allowed during the webinar as well as in the end. The questions can be asked using the chat, both in Google Meet and in YouTube. We're going directly in YouTube as well. Questions can be also written in Portuguese, and I will translate the questions to English. Today, we have the great honor to listen to Professor William Daniel Phillips, who was awarded with the 1997 Nobel Prize in Physics, together with Stephen Chu and Claude Cohen-Tanucci, for development of methods to cool and trap atoms with laser light. Our special guest is a distinguished University and College Park professor of physics at the University of Maryland and a distinguished member of the National Institute of Standards and Metrology in the United States of America. Apart from the Nobel Prize in Physics, Professor Phillips has received several distinctions, including the 1998 Arthur Trollope Prize in Laser Science, the 2000 Richtmeier Award of the American Association of Physics Teachers, the 2002 NIST Condom Award, the 2004 has been appointed as an academician of the Pontifical Academy of Sciences. In 2005, has received the Presidential Rank Award, and in 2006, the Service to America Award for his career achievement. Professor Bill Phillips is a fellow of the American Physical Society, a fellow and honorary member of the Optical Society of America, and a member of the National Academy of Sciences in the United States of America. Professor Phillips has visited Brazil several times, including in 2011, when he traveled to Amazonia together with Professor Vanderlei Banhato, that is here with us today, and gave an outreach lecture in a public school located near the Negro River. Today, Professor Bill Phillips' colloquium will be about a new measure, the revolutionary reform of the metric system. And I should not make you wait further before listening to him. Professor Phillips, thank you very much once more for having accepted our invitation. We're very honored. The audience is yours.
Thank you very much for that that kind introduction. Let's go to the slides now. Okay, so as you heard, I'm going to talk about the reform of the metric system, and as you also heard, I'm from both the National Institute of Standards and Technology. This is the National Metrology Institute of the United States, and I'm also from the University of Maryland. And at NIST, I'm part of the Laser Cooling and Trapping Group, which is led by Gretchen Campbell and also has Paulette, Trey Porto, Ian Spielman, Ida Tietzinga, and Charles Clark as members. And it's a great pleasure and an honor for me to work with them on a daily basis. Again, I want to encourage you to ask questions, put them into the chat or the question portal, and some of the questions we may answer as we go along, and we'll try to answer all the questions at the end. And if I were with you in person, I would offer you a prize for asking a question. But unfortunately, I'm not here to give you the prize. The prize is a wallet card of the fundamental constants of nature. And here is a picture of what that wallet card looks like. And one of the things that I want to call your attention to is the fact that all of the constants that appear on this side of the card, and there are others on the other side, all of those constants are exact. They have no uncertainty at all. The speed of light, Planck's constant, the charge on the electron are all exact quantities. That did not used to be the case. And in fact, much of what I'm going to be talking about today about this reform of the metric system has to do with why it is that these constants are exact. We have many other constants that are not exact, but those ones are. And it has to do with the fact that there has been a revolution in metrology. On the 20th of May, 2019, the world experienced the greatest revolution in measurement since the French Revolution. And that revolution is a change to the international system of units, the international metric system, which in French is referred to as the Système International d'Unité, and therefore we call it the SI. And these are the 7 base units of the SI. Everything that we measure is based on some combination of kilogram, meter, second, ampere, Kelvin, mole, and candela. And the change that happened, this revolutionary change, is that every one of those constants are now defined by fixing the values of fundamental constants of nature. And in order to understand how that can be, how it is that we can define a unit of measure by fixing a fundamental constant of nature, and with apologies to the late, great Stephen Hawking, I would like to bring you a short history of length. And the reason I'm doing this is because length, even before this revolutionary change a year ago in May, length had already been defined by defining a constant of nature. So let's recall a little bit about the history of length as a unit of measure. The original standard for length measurements was the human body. A foot was a foot. A cubit was the distance between the elbow and the tip of the finger. A yard was the distance from the center of the body, the nose, to the fingertip. A fathom was the wingspan of a person. This was wonderful. It was extremely convenient because you always had your standard of measurement with you. The problem was that it wasn't very consistent. If you were buying fabric from a short fabric merchant, you might not get as much fabric as you had expected. And so people tried to find ways to make the system of measurement more consistent. One way was not to use the body of whatever person was at hand, but to use a particular body, usually the body of the monarch. In ancient Egypt, it was the body of the pharaoh, and the standard of measurement was the royal cubit, the distance between the pharaoh's elbow and his fingers. That was the standard of measurement. But this wasn't so convenient because you didn't have the pharaoh at hand. So what happened was in ancient Egypt was, and I hope you can see my cursor, maybe I can even change my, the thing that I'm pointing with. There we go. Maybe that's, well, okay, I hope that's a little easier to see. They made a granite artifact that was the length of the pharaoh's forearm, and this became the standard of measurement for Egypt. And people out in the field, people who were building the pyramids, for example, would use secondary standards, standards of length that were in wood. And they were required to calibrate these wood standards against the stone standard every month, and there was a death penalty for non-compliance. These people were really serious about metrology. And they were so serious that they did a really excellent job in building the pyramids. The bases of the pyramids are consistent with one another to a small fraction of 1%. They're square to 12 arc seconds. They really did a good job of measurement. They were that serious. And this idea of making an artifact was something that became common throughout the world. In Europe, for example, it was very common for the standard of length to be set into the stone wall of the town square, where everyone would have access to it. Now, this was very convenient for the people who lived in that town, but the problem was that things would vary from one town to another. Here, you see the standard of a fathom in the city of Regensburg, and this looks like it would be a really good place to buy fabric because the fathom is quite long. But this standard was different in the surrounding towns of Bavaria around Regensburg. So this was a problem that everyone realized needed to be addressed. And finally, at the time of the French Revolution, the French revolutionaries decided they would solve this problem by coming up with a new unit of measure that they called the meter, and with a definition that would be good for everyone. And so the new definition of the meter was that it was 1/10,000,000th of the distance between the pole and the equator along a meridian that went through Paris. And in order to finalize this definition, they sent out teams of surveyors to survey the distance between Dunkirk and Barcelona. And then they extrapolated to the entire meridian. And this became the standard of measurement. But it turned out that this dream that they had, which was memorialized in this medal that you see here, of producing a system of measurement that would be good for all time and for all people. And you see this allegorical character measuring the earth, which is exactly what they did. The trouble was that it, again, was not very convenient. And so they did exactly the same thing as the ancient Egyptians did. They made an artifact. And here is a picture of the artifact, the meter of the archives, which was installed in the archives of Paris in 1799. This was the length of the meter that they had obtained doing this, this survey, but they made an artifact for the same reasons that the Egyptians did, because it was more convenient. And later, in 1875, when the countries of the world gathered together to sign the Treaty of the Meter, the Convention du Mètre, they authorized the creation of still a new standard. This was a line standard, and the meter was defined as being the distance between a scratch here and a scratch here on the other end of this bar. And this was better than the old N standard. In the old N standard, the distance of a meter was the distance between this end of the bar and that end of the bar. And the trouble with that definition was that in order to realize it, you had to touch the end and you could wear it down. Here, you could look at it with a microscope and determine what the distance between these two scratches was relative to some other thing that you were trying to measure. The trouble with this was that almost as soon as this definition was in place, people realized that they had even more accurate ways of comparing lengths. People had discovered that light was a wave, and they'd made devices called interferometers that allowed them to measure length in terms of the wavelength of light. And so in this cartoon version of a Michelson interferometer, you see that if you have a source of light from some sort of a lamp, the light travels into the interferometer. It gets split here at this beam splitter. Some of the light goes this way, some of the light goes this way. And when this mirror is moved, the interference pattern that you see here changes from having a dark spot at the center to having a bright spot at the center when this mirror is moved by only a quarter of a wavelength of light. That's a few hundred nanometers. And compared to the width of the scratch that is on the meter bar, which is at least several microns wide and rather ugly, because after all, it's a scratch, it meant that people were able to measure lengths using the wavelength of light far better than they could using the actual definition of length, which is based on the distance between those two scratches. And so people started to use the wavelength of light as a sort of de facto standard. It was not the official legal definition of length, but everyone used it because it was far more accurate than the legal definition. But it wasn't real meters. And eventually they decided they had to change the definition. And so in 1960, which incidentally is the year that the laser was invented, they redefined what a meter was by saying that a meter was a certain number of wavelengths of light coming from this krypton lamp that we have here. And unfortunately, as so often happens in these kinds of meetings, my phone is ringing, and I'm just going to make it stop. And whoever is calling me is going to be upset. Okay. Sorry about that, folks. So they redefined the meter in 1960 to be a certain number of wavelengths of light from a krypton lamp. But almost as soon as they did that, people found that the purity of light from this lamp was not as good as the purity of light that came from a laser. And so people were able to make still better measurements than were possible using the wavelength of light from a lamp like this by using a laser, because the light coming out of the laser was so pure. And again, people started to use laser light as a de facto standard of length. And here's a picture of one of those helium neon lasers stabilized to an absorption in molecular iodine. And this became, again, the unofficial standard of length, not the metric system, not the SI definition of the meter, but a better way of comparing lengths that was being used as a de facto standard. And so it became clear, just as it had been at any number of times in the past, we needed a new definition that took advantage of the better technology, in this case, lasers. And the obvious thing to do would have been to redefine the meter in terms of the wavelength of light coming from an iodine-stabilized helium neon laser. Fortunately for us, they did not take that obvious choice. Fortunately, instead, they took a more brilliant choice. And that brilliant choice was to define the meter by defining the speed of light. What did that make the new definition? The new definition was that the meter is the length of the path traveled by light in vacuum during a time interval of some fraction of a second. And that fraction of a second is the inverse of the speed of light, because by definition, it is the distance light travels in 1 meter. And we have this universal relationship that says that the wavelength times the frequency is equal to the speed. So that means if you have any light you want and you can measure the frequency, then you immediately know what the wavelength is if you've defined the speed of light. And the beauty is that if someone makes a better laser with a more pure light, and they did, or if someone invents a new way of measuring the frequency of light, and they did, then all of these improvements are immediately incorporated into the definition. So we no longer have the situation where when a new technology comes along, like the invention of the laser or like the invention of interferometry, that we need to change the definition in order to make use of that new technology. By defining a constant of nature, in this case, the speed of light, we take automatically into account all possible improvements. This was a truly brilliant definition. And on the 20th of May, 2019, the international community brought this same beauty to the kilogram and, for that matter, to the ampere, the Kelvin, and the mole. Well, why was that necessary and how was it done? Well, in order to examine that, let's review a light history of mass. These are stones that were used in ancient Babylonia to be the standards of mass. When you wanted to determine whether a certain amount of grain weighed a certain amount or whether some jewel weighed a certain amount, they could be compared against these standard stones. One of these stones, I forget which one, is called a shekel, which is a name you may have heard as an ancient unit of mass. But these standards of mass, these artifacts, these manufactured objects, had the same problem that the old artifact standards of length had. They were different from one place to another. And so As in the case of length, during the French Revolution, it was decided that there should be a new unit of mass. In this case, the kilogram. And the definition of the mass of a kilogram was that it was the mass of 1 liter of water. And 1 liter of water was a cube that was 1/10 of a meter on a side, 1 cubic decimeter. Well, that was wonderful. It was based on the meter, which was this new unit of length. Water is easily available, and so it should be available to everybody. But there were problems. It wasn't so easy to have just 1 liter of water. There were problems with the way in which water wet the surfaces. Water at different temperatures had different densities. There could be impurities in the water. And so the French revolutionaries used the same technique that they had used in the case of the meter. They created an artifact. And you see that very artifact that was created in 1799 is right here. I visited the archives of France a little while ago, and I got to hold the box in which the kilogram of the archives is kept. And that is the original box that was created in 1799. So again, we have this return to the ancient practice of creating an artifact. And as in the case of the meter, in 1875, at the International Treaty of the Meter, a new artifact was made, a cylinder in platinum iridium. And that became the standard of mass for the entire world, because the countries of the world agreed, as with the meter, that this kilogram would become the standard of measurement for all of the countries that adopted the metric system. And as it turns out, until a year ago in May, this was still the definition of the kilogram. It was the last artifact. The fact that here's another picture of me with the kilogram inside this this bell jar on the 125th anniversary of that international treaty. But the problem was that here we have, in the 20th century, in the 21st century, we are using an artifact that was made in the 19th century, based on an artifact that was made in the 18th century, the kilogram of the archives. We are using it in the 21st century. This situation is so scandalous that comic strips in US newspapers would make fun of it. Here is one of those comic strips. In this comic, a little girl in this school is complaining to her science teacher, asking, isn't it true that we've redefined the meter to be based on the speed of light? And he says yes, because the previous definition based on the dimensions of the Earth was inaccurate. And she asks about time, and we haven't talked about time yet, but it used to be a certain fraction of a solar day, and now it's the oscillations of a cesium atom, and the teacher agrees, yes. Then why haven't we changed the definition of the kilogram? It's still the mass of the international prototype of the kilogram, an actual lump of stuff that's stored somewhere. And the teacher finds this so unsettling that he finally says that he needs to lie down, and the girl tells her friend, you see, I told you that there were ways of getting to him. Well, we're not worried about upsetting the high school science teachers, but this is a problem. Just as illustrated there in that cartoon, that if someone were to sneak in and shave off a piece of the kilogram, then it would change the definition of mass for the entire world. Well, no one has done that, but the mass of that kilogram is in fact changing nevertheless. Here is a plot of a number of copies of the kilogram compared to the actual kilogram itself over the years. And what you can see is that the mass of most of the other kilograms in the world has been increasing. Now that makes you think probably what is happening is that the mass of the international prototype of the kilogram is decreasing for some reason. But it cannot. By law, the mass of the international prototype of the kilogram is always a kilogram. And this is a completely intolerable situation. And in order to fix this scandal in international metrology, we needed to have a new definition of the meter, and we wanted to use the same beautiful approach that had been used when we redefined the meter. That is, we need a new definition for the kilogram, and we want to use the same beautiful approach that we used for redefining the meter. We want to define a constant of nature. So, what constant do we use? Well, to illustrate that, let me remind you of what is almost certainly the most famous physics equation in all of history, E equals mc squared, where E represents the energy of an object at rest, m is the mass of that object, and c is the speed of light. Now, let me add to that another famous equation, not quite as famous. The energy of a photon is equal to the frequency of the light from which that photon derives times Planck's constant. Now, what does that mean? If we combine these two equations, then we find that if we solve for mass, we find that the mass is equal to Planck's constant times the frequency divided by c squared. What does that mean? It means if we have some object and it emits a photon of frequency f, or it absorbs a photon of frequency f, that its mass will change by this amount. Now, we're not going to use as a standard of mass the weight of a photon. That's too hard, and we can't do it well enough. But using this definition, by fixing the value of Planck's constant, you see, if you fix the value of Planck's constant, and you measure these other things, you measure the frequency, and we already fixed the value of c, then you've got a definition of mass. And by using this idea of fixing Planck's constant, and because of a brilliant idea from this gentleman, Brian Kibble, we can realize the new definition of the kilogram by defining Planck's constant and using an electromechanical device known as the Kibble balance or the Watt balance. So here I've got a movie that shows how this works. So let's run the movie. Okay. So I think that it's not playing my movie, maybe because I've got a different pointer. So let's just play the movie now. So in this movie, what I invite you to do is remember the traditional way in which we measure things. If we have an unknown mass over here, the way we measure its mass is we put some known masses over here derived from the international prototype of the kilogram. And when the balance balances, we know how much mass was required to balance the unknown mass, and that's how everybody measures mass. Now I want you to think about an alternative way of measuring mass that should work just as well. Instead of balancing our mass with other known masses, we balance it with the electromagnetic force from a current-carrying wire in a magnetic field. So if we have some magnetic field here, illustrated by these red lines of magnetic field, and we have a coil that has some current in it, and if we can measure the current very well, and we can, and if we could measure the magnetic field very well, which we cannot, and if we knew where all the wires were on this coil, which is very difficult to do, if we could do all of those things, then we could determine the value of this unknown mass by comparing the force of gravity on that unknown mass to the electromagnetic force on this side of the balance. And the trouble is that we don't know those things like the magnetic field and the placement of the wires well enough to make this work. But here's where the genius of Brian Kibble comes in. Kibble said, take that coil of wire, whose positions of the wire you don't know, and take the wires out and connect the wires to a voltmeter. If you measure the voltage generated when this coil moves in the magnetic field, and you don't know the magnetic field, and you don't know the placement of all the wires, but if you move the coil of wire and measure its velocity, and measure the voltage that's generated, so we call this the velocity mode of the experiment, because we're allowing the coil to move at a velocity that we measure the voltage. If you do that, that gives you all the information that you need that you didn't have about what the magnetic field is and what the placement of the wires is. And so you make that measurement. And then you make the other measurement that you've already made. That is, you put current in the wire and you measure the force by comparing it to a mass, the gravitational force of another mass, and putting these things together, we can effectively measure a mass or realize the new definition of the kilogram. So let's just see how and why that works. So what we're going to do is we're going to take the mass that was balancing the force from this coil of wire. We multiply that by the acceleration of gravity. That gives us the gravitational force. We multiply it by the velocity that we measure when we're doing the velocity part of the experiment. And that has got to be equal to the current that we used in the weighing part of the experiment and the voltage that we measured in the velocity part of the experiment. So each of these sides of the equations has something from the velocity mode, like the voltage or the velocity, and something from the weighing mode, like the current or the mass. And the reason these two things have to be equal is that this side of the equation is mechanical power, and this side of the equation is electrical power, and in a proper system of units, those two things have to be equal. Force times velocity has to be equal to current times voltage if we've got a good system of units. So we solve this equation for the mass, and we find that the mass that we have on the other side of the balance is equal to the current from the weighing mode, the voltage from the velocity mode divided by the acceleration of gravity, and the velocity from the velocity mode. But now you may ask, how does this relate to Planck's constant? And it has to do with the way in which, in modern times, we measure the current and the voltage. And this is due to two wonderful quantum effects known as the quantum Hall effect and the Josephson effect. And the people who discovered these things are Brian Josephson and Klaus von Klitzing. And here I am, sandwiched between these two giants of electrical metrology. So what Josephson gave us was the Josephson constant, which tells us how many hertz per volt we have when we have an AC current flowing through a superconducting junction. And I wish I had time to tell you all about that, but ask me in the questions if you would like to know more about it. So we get hertz per volt from Josephson. From von Klitzing, we get a certain resistance in a solid state device is equal to a certain number of ohms, which we now call the von Klitzing constant. And if we measure things in this way, the voltage is proportional to h over 2e, because 2e over h is the hertz per volt of the Josephson constant. So we have h over 2e there. And when we measure the current, we do it by putting current through a resistor. The resistor creates a voltage that's measured in h over 2e, and the resistance is in h over e squared. And when we cancel everything out, we find that the mass is proportional to Planck's constant, which is exactly what we wanted. So that's how we get masses by defining Planck's constant. And here is a picture of one of those Kibble balances, the one that we have at NIST. And this balance can realize the definition of the kilogram to about a part in 10 to the 8th, which is better than the changes that happen from year to year due to whatever dirt is getting on or coming off of the kilogram, which we don't really understand. And here is part of the team that did the experiments that made possible this redefinition of the kilogram. And the thing that I want you to note about these wonderful heroic scientists is they're so confident in their result that they have tattooed the new values of the fundamental constants on their arms, even before the international agreement that this would be the way we would change the international metric system. Now, it turns out that this Kibble balance is not the only way in which you can realize the new definition of the kilogram by defining Planck's constant. Another technique, which is mainly associated with the National Standards Laboratory of Germany, has made a perfect silicon sphere, or a near perfect silicon sphere, and this allows us to convert atomic masses to macroscopic masses. And I wish I had time to tell you the details of how that works, so please ask me about it later, and I'll be happy to explain how we can realize the kilogram using this perfect silicon sphere. All over the world, people are using silicon spheres, or they're using Kibble balances to realize the new definition of the kilogram. First to measure Planck's constant, and then to come up with a way of realizing the new definition of the kilogram. And so we had, on the 20th of May, this new definition went into effect. But 2 or 3 other fundamental constants were defined as well. For example, by defining the charge of the electron, we have a new definition of the ampere. It used to be that the definition of the ampere was that it was the current which, in 2 infinitely long straight wires a meter apart, would produce a force of 2 × 10⁻⁷ newtons per meter. Now the ampere is simply a certain number of electrons per second. Now, here's the wonderful thing. If you define the charge in the electron and you define Planck's constant, then the Josephson constant, 2a/h, and the von Klitzing constant, h/2e, are both exact, and we now have exact ways of making all of our electrical measurements. 2 more units, the mole. It used to be that the mole was the amount of substance that had a number of entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. Now it's simply a number. In other words, we have defined the Avogadro constant. Avogadro's number is now a defined quantity. And finally, the Kelvin. It used to be that the Kelvin was the unit of temperature that was 1/273.16 degrees of the triple point of water. And now, instead of using water as the standard, we have defined the Boltzmann constant. So now the Kelvin scale of temperatures is defined in terms of the thermal energy that the matter constituents have. And we've done that by defining the Boltzmann constant. So now we seem to have realized this dream of the French Revolution that brought this new unit of measure called the meter, and wanted this to be the measure of all things, for example, of the kilogram, and had this dream of bringing this unified system of measurement, not just to France, but to the entire world. And then on May 20th, the anniversary of the signing of the 1875 International Treaty of the Meter, we had this additional revolution that defined 4 more quantities by fixing constants of nature. And so this revolutionary spirit of liberty leading the people that you see here in this amazing painting by Delacroix means that the world is finally free of artifact standards of measurement. We no longer depend upon the kilogram. We now have this system of units where the kilogram is defined in terms of Planck's constant, and the meter in terms of the speed of light, the second in terms of the hyperfine frequency of cesium, the ampere in terms of the electron charge, the Kelvin in terms of the Boltzmann constant, and the mole in terms of Avogadro's number. And what it means is that a little wallet card can have all of the definitions that are used in the international system of units. And so it seems that the dream of the French revolutionaries, that we should have a system of measurement good for all time and for all people, is something that we finally have achieved. And so to celebrate that, to actually, I want to show you a movie that was made at the, to be shown at the 26th conference, General Conference on Weights and Measures, which officially approved this adoption, which was to take place in the following May. So let me play this movie that was done right after the vote in which 60 countries from the world all agreed that they were going to change these definitions of the metric system.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community. At times, it seemed
Impossible.
accurate,
Precise measurement.
anytime,
Anywhere. Thanks.
we did it. Ce l'abbiamo fatta. You have this special. No, grazie. Lei sia buoni. Bismillah. Welcome, guys.
Het is ons gelukt.
Yes, definitely.
Interferometers.
Nic ma to uczynili.
Dokázali to.
Congratulations.
Carmina.
Felicitazioni.
Basalto. Congratulazioni.
Sente le province. Mama. Success. Parabéns. Congrega. Momento.
Anguida.
Conexão global.
Mabruk.
Capaz.
Amico.
Felicitations. Congratulations.
When I see that movie, and I've seen it many times, I still become emotional, because to think that 60 countries of the world could agree unanimously on anything is really amazing. And it's a wonderful thing to know that we now have this wonderful new system in which we've wrapped up the international system of units in this lovely package where we've defined constants of nature for all time, for all people. But is it really for all time? What about time itself? What about the definition of the second? Right now, the definition of the second is embodied in the definition that the hyperfine frequency of cesium is 9.1926317 gigahertz. The trouble is that today, people are measuring this to about a part in 10 to the 16, probably the best thing that's measured, but using different atoms and different transitions in laboratories all around the world. Here is shown the NIST laboratory in Boulder, Colorado, are making these measurements to a few parts in 10 to the 18. In fact, with aluminum ions, the accuracy of these measurements is parts in 10 to the 19. And so it seems that we're going to have to change the definition of time itself. As before, we changed it from something having to do with the rotation of the Earth, and we changed length and mass, we're going to have to change time. But the question is how? There are many, many atoms and many different transitions, all of which have their own advantages and disadvantages. And whatever we do finally decide upon, and we will, there's no guarantee that there won't be still a better transition found, better techniques for measuring that, that frequency. And it doesn't seem that we're ever going to be able to achieve what we've achieved with the other units of measure, something that will be good for all time. And so the future of the SI is wonderful, but the future of time, only time will tell. Thank you very much.
So thank you, Professor William Phillips, very much for your wonderful talk. And before we proceed, I'll just ask everybody to turn on their microphones to a round of applause in acknowledgement for this very nice talk. Thank you very much, Professor.
Thank you. Well, am I back on camera? Can you see me on camera now?
Yes, yes.
Well, then
So,
I want to show you, because I didn't have a chance to do this because I was showing you the slides. Here is a box that looks very much like the box that held the kilogram of the archives, and in it I have a model of the international prototype of the kilogram. So just so you can see what a kilogram really looks like sort of up close and how small it is, because of course the density of platinum is so big. And I'm wearing white gloves to emphasize that if this really were the kilogram, and if I were to leave a fingerprint on it, all of you would lose weight by definition. But now that's changed. That won't happen anymore.
Okay, thank you very much, Professor, once again. So we have questions, but before we proceed to the questions, let me just give you an overview of the audience that has been attending to your talk. So both from the YouTube and from the Google Meet, we have participants from all the 5 regions of Brazil, right, including states of Amapá, that is in the top north of Brazil, Pará, obviously. Then in the northeast, for instance, we have people from Pernambuco, from the central part of Brazil, including the Brazilian capital, and also from the southeast Brazilian region, including Minas Gerais, Rio de Janeiro, and São Paulo, cities like Juiz de Fora, Niterói, São Carlos, like Vanderlei Banhato, for instance, people from Joinville in Santa Catarina in the south of Brazil, and many others. We have, obviously, since this webinar is organized by our graduate program, we have students, teachers, postdocs, and professors of the Federal University of Pará, like, for instance, Castimeiras, Eleutério Newton, and even the director of the Center for Exact and Natural Science, Professor Marcos Diniz. We have also professors from all around Brazil, like Maurício Coutinho Filho from the University of Pernambuco, José Ademir Salles Lima, and Vanderlei Banhato, as I said, from UFPA. We have Satis Kumar Vieira from University of Rio de Janeiro, and also people from abroad, as we mentioned, Professor Michael Kosterlitz from USA, from North America, right, and other South American countries as well. Not everybody wants to write their names and the places where they are speaking from, right? So, but this is, I think, enough for you to have an overview of the attendance. So the first question I have registered from is from Satish Kumar, that is attending from the Federal University of Rio de Janeiro. So Satish, do you want to turn on your microphone and make the question yourself?
Thank you, Dr. Phillips. It was a wonderful talk. I have 2 questions. Before I ask the question, I would like to compliment you on your background. It's fantastic.
Well, it's just it's simply one of the standard backgrounds that you get with this video platform.
That's fantastic. With your beard and everything, it feels like I'm speaking to a god. Okay?
Well, the beard, you see, is to give a physical record of just how long it has been since this pandemic has started. I haven't cut my beard since I had to start the lockdown.
That's the measure of the lockdown.
Exactly.
That gives you the measurement of the length of the lockdown period. So speaking, I have 2 questions. The first one about the definition of the second, of the transition in the cesium atom, right? So we know from general relativity that this time is sensitive to gravitational field, right? So for example, if you define this as a certain number of the seconds, the wavelengths, right? So in your laboratory, it would be different in my laboratory.
Yes.
So what's the caveat that goes into this?
Yeah, okay. That's the first question. I'm so glad you asked that question. So because of general relativity, as you point out, a clock will tick at different rates depending upon where it is in the gravitational field. Now, the effect is small, but clocks are so good that it matters. So the amount of change is about 1 part in 10 to the 16 per meter. Now, the clocks are good to about a part in 10 to the 16. So this is a huge difference for clocks that are in the mountains compared to clocks that are at sea level. So the definition of the second includes what we sometimes call a mise en pratique, a way of putting into practice the definition. And it specifies that what we mean by the hyperfine frequency of cesium is measured at the position in the gravitational potential that corresponds to mean sea level. So that's how we get around the general gravity problem. But we actually use the general the general theory of relativity with these newer clocks, the ones that are good to a part in 10 to the 18. That's just 1 centimeter. These are now being used for geodesy. That is, people will move one of the clocks around and map out the gravitational potential relative to a clock that is fixed. Now, the problem is, what happens when we redefine the second so that the second can be realized to better than a part in 10 to the 8th? I'm sorry, a part in 10 to the 18. That means we have to control the vertical displacement to better than 1 centimeter. What happens when the sea level rises because of global warming? What happens when there are shifts in the Earth's crust due to earthquakes? This is something that really hasn't been considered yet. So we're going to face some really interesting questions as we make our standards of time even better. But here's another point that goes to your question. If you are measuring always on the Earth, then it's perfectly fine to refer your measurements to some particular place, like mean sea level. But if you're measuring astrophysical quantities, then things are different. Millisecond pulsars that come from rotating neutron stars or from binary stars that are billions of light years away, they're not referencing to the Earth's gravity. And that means that if you want to measure them, you've got to take into account the fact that Earth changes its total gravitational potential because of its changing distance to the sun. And other planets in the solar system, their position will affect the clock rate relative to the pulsars. So people have to recenter the reference frame for these clocks to the center of the solar system in order to make sense of these astrophysical observations. So your question has lots and lots of layers to it.
Thank you so much. That's a beautiful answer. Second question, again related to gravity. So we used already the speed of light, sacred constant. I'm a theoretical physicist. For me, the 4 constants are very sacred: the speed of light constant, Boltzmann constant, and universal gravitational constant. You made use of the Frey, but not the universal gravitational constant.
Yeah.
Why?
Yeah. Okay. So, very good question again. So why not use the universal gravitational constant? Well, the reason is that, for one thing, we don't know it well enough. The measurements, the best measurements of the universal gravitational constant are about 1 part in 10 to the 5th. It is the least well-known of all of the fundamental constants of nature. Why? Because in order to measure it, you have to measure forces, purely gravitational forces, between objects that you keep in your laboratory. And it's very difficult because these are extremely small forces compared to the force of gravity, for example, from the Earth on those objects. And furthermore, it appears that we don't really understand how to make these measurements very well. People have made measurements of the universal gravitational constant that they claim are good to, say, a part in 10 to the 5th or a few parts in 10 to the 5th, but different laboratories making the same claim but using different techniques for measuring it are sometimes different by tens of standard deviations. Now, that should never happen. And what it means is we don't understand what we're doing. And we're trying to work that out, but at this point, we are so far away, at least 3 orders of magnitude away, and probably more, from being able to define the kilogram in terms of the universal gravitational constant, that essentially we do not consider it. The situation with the Newton's gravitational constant is truly scandalous, that we don't know it any better than we do, and that there's so much disagreement of measurements of this constant.
Although that was the first constant to be known among these four.
Yes, isn't that
I thought we have done a better job with the
and we're not doing much better than Cavendish did.
With the-
That's the thing that's so frustrating.
experiments. But
Okay.
Thank you so much.
Okay, so thank you, Satish, very much for your questions. Thank you, Professor Phillips, for your answers. I think Vanderlei Bagnato, Professor Vanderlei Bagnato has a question. Vanderlei, do you want to make it yourself?
Yeah, I'm going to try to be very fast. I know there are many people who want to ask Bill a question. My first question, Bill, is if we define the kilo based on the silicon sphere, somehow are not, don't you think that we are creating just a more fancy artifact?
Okay, that's a very good question. And I'm glad you asked it, because I think it helps to illustrate what's going on here. Probably I should share my screen to answer this question. So let's see, if I go here and go to this window, and then we go, let's see, where, probably here, and then there, and now let's see, there's another one of the standard Zoom problems. Okay, now I see that what I have to do is, yeah, I want to show this, this picture. Okay, so here's one of the ways of getting to a definition of mass based on the silicon sphere. And by the way, I should say, Vanderlei knows perfectly well what the answer to this question is, but he's asked it for the benefit of everyone else in the audience so that you can understand how this other way of realizing the kilogram comes in. Vanderlei is the past chair of the Commission of the International Union of Pure and Applied Physics, that has responsibility for constants and units. And in that capacity, we've been promoting this new metric system, and he's doing his job still in promoting it to all of you. So here is what the way it starts. Imagine an atom. Typically, this is an atom of rubidium, but it could be anything. The atom absorbs a single photon from a laser whose frequency we know very well, and that means that we know the energy of this photon very well. We also know the momentum of the photon because it's just equal to Planck's constant divided by the wavelength, and of course if we know the frequency, we know the wavelength because we've defined the speed of light. So because we know what the momentum is, we know that after the atom absorbs the photon, it will be moving with a certain velocity such that the velocity of the atom is equal to the momentum of the photon, and we can calculate what that velocity of the atom is. That is, the mass of the atom times the velocity of the atom is equal to the momentum of the photon. And if we solve for the mass, we now know the mass in terms of Planck's constant and the wavelength of the light, and we know the wavelength of the light because we know the frequency. So that means we now know what the mass of this atom is in kilograms, okay? Now, the magic of the silicon sphere is that it allows us to take the mass of the atom in kilograms and convert it to a macroscopic mass that's actually something that's useful. So we do some experiments to measure mass ratios, and we measure the ratio of the silicon atom mass to the rubidium atom mass, and then we grow this perfect crystal of silicon and machine it and polish it into a perfect sphere. And this is the most perfectly spherical object in the entire world. And then by X-ray interferometry, we measure the spacing between the silicon atoms in meters. So when we measure the size of this thing in meters, we essentially have counted how many silicon atoms there are in this sphere. And since we now know what the mass of silicon is relative to rubidium, and we know what the mass of rubidium is relative to in kilograms, you see, we now know what the mass of this thing is in kilograms. And it's not an artifact because, unlike an artifact, if you lost the artifact, then you'd have lost everything. You've lost all your memory of what a kilogram is. But here you can always make a new one because all you need is silicon, and there's plenty of that, and the skill to make a perfect crystal and to make a perfect sphere. And so it's not really a new artifact any more than the Kibble balance creates a new artifact. Remember, from a practical point of view, people are still going to be using platinum spheres, platinum cylinders as secondary standards. And in a certain sense, this silicon sphere becomes a secondary standard. The primary standard is conceptual. The primary standard is the value of Planck's constant.
Okay, a very fast second question,
Sure.
if you allow me. We know that if you look into the code data, which is the table you show to everybody, there is a definition of the electron charge. There is a definition for the Planck's constant, but there is also a definition for the von Klitzen constant. That's dependent on the electron and the Planck's constant. So is that a redundance? We have to have the von Klitzen as a fundamental constant?
Yeah. Okay. So if you look down here, there's the constant that you're interested in, the von Klitzen constant.
Yeah.
No, here it is, right here. Okay. Now you'll notice that it gives all these digits and then ... And that's because its value is based on h over e squared. H is, you see, h is defined to a certain number of digits. E is defined to a certain number of digits. H over e squared is going to be a repeating decimal, and the decimal will repeat, I forget how many times. It'll take like 1,000,000 digits before it repeats. I think that von Klitzen calculated how long it would be before it repeats. It's a really long time. So it's not a new constant. It's just on here for the convenience of the user. But it's exact, but these extra digits are something you'll have to calculate with your own calculator, but you easily can using E and H.
Thank you. Thank you, Bill.
A pleasure.
Wonderful talk.
Thank you.
So thank you, Professor Vanderlei Banhato. Thank you, Professor Bill Phillips, for your answers. I don't know if you were planning to share your screen. You know that you're not sharing, right?
Oh, I thought I was. I'm sorry.
No problem.
You should. Yeah, I thought I was sharing it. Oh dear.
Yeah, because but well, I think we understood even if you were not sharing.
Yeah, I apologize for that. And now I'm trying to figure out how to get back to where I was. So you're. Okay.
Yeah, if you want to share, you have to go down with your mouse and present now and all those steps.
Yeah,
remember?
I thought I did that, and I guess I probably didn't do the last step.
But
now?
Well, it's up to you. While in the meantime, let me tell you. Let me make a question that we have from YouTube. So from a master student from Federal University of Pará. So it's Juan Lima. He is attending from the YouTube, as many others, and he says, Professor Phillips, what about the International Unit of Intensity of Light, the candela?
Yeah.
Has that ever been considered to be a fundamental thing, or has it transcended to such a stand along with those units? I mean, I think you understood what.
Yes, I understand very well, and I have to admit that the question is an exceptionally good question, and it's also a bit embarrassing because, okay, so now am I sharing my screen? Can you see the shared screen?
Yes, sir.
Okay, great. So now let's go to this one right here, luminous efficacy. And what that says is that luminous efficacy is 683 lumens per watt. So a lumen is something that's related to a candela. You just have to, it just has some solid angles in it. But so what is this about? I'm pretty sure that the questioner understands what the luminous efficacy is, but let me explain it for the rest of the audience. The human eye perceives brightness in a way that depends upon the wavelength of the light, and as a result of that, if you want to have a uniform description of how bright something is, then you have to take into account this variation of the human eye in its sensitivity. And the human eye is most sensitive in the green, and then it falls off as you go toward the red or the blue. When you go to the store and buy a light bulb, it will say on the light bulb how many lumens it has. And the question is, how do we relate that to something that we can measure in the laboratory? And the answer is that they've defined this quantity of luminous efficacy, saying that a lumen corresponds to a certain intensity of light of a certain color, where that intensity is in watts per square meter. Okay? So if it's a different color, then people have to judge whether this light intensity is stronger or weaker than this green light intensity. And they've taken lots and lots of people all over the world to try to develop these relationships. And then they've embodied this into this definition of luminous efficacy. So as the questioner implied, this really is not a fundamental constant of nature. This is something that has to do with the way in which people perceive light. And so in a certain sense, it is the most human of all of the units of measure, but it's also the least consistent and physical. And so you might very well ask, why is it part of the base units of the International System of Units? And the answer is, it's probably political. That the people who sell light bulbs want to have a standard that is embodied in the International System of Units, and that's why it's there. And I don't have a better answer, but I do want to ask, have I answered your question sufficiently?
That's a tricky question, Professor, because you know he's in YouTube, so I'll check it in a minute or so. But there's a delay. I'll try to take this into account. So in the middle, let me put a question that has been written by John Freddy Contreras Rojas. I hope I have spelled correct. I think he's speaking from, he's participating from Colombia. He asked me to read the question for you. He says, Professor, do you think that an analytical definition can be reached in a certain way, abstract, that allows us to measure or define what time is, or otherwise? Can a definition of fundamental constant be formalized without having to depend, in some sense, of time? Is the illusion of time necessarily necessary? He ends by that.
Yeah, okay, so that's a very good question, and people have been asking the question about what is time, and is time an illusion? I think people have been asking that question since at least the beginning of human time. So the question about the illusion of time is not one that I'm really capable of addressing. I would rather take Einstein's answer to the question of what is time and simply say that time is what a clock measures. And we have really excellent atomic clocks that measure time, but it always seems that there's something better. So part of the question has to do is, can we come up with a definition that is as beautiful as the definitions that we've had for the meter or for the kilogram? Can we have a similarly beautiful definition for time that will not be subject to changes in technology? Can we have something that's more fundamental than having it tied to a particular atom? So one possibility that people have advanced is we could define the Rydberg constant. Now, the Rydberg constant gives us the scale of energies for the hydrogen atom. The trouble with that is that we measure today, in the SI, we measure time to a part in 10 to the 16, and soon maybe within another decade, we will measure time to within a part in 10 to the 18 in the SI. Whereas the Rydberg constant is known to many orders of magnitude less well than we can measure time even now, let alone for new definitions. Now, why is the Rydberg constant not known? Well, because we don't understand the hydrogen atom well enough. We can measure the hydrogen atom, but we don't understand it very well. We don't understand the nucleus. The nucleus is a proton. The proton is not an elementary particle. That means that the structure of the proton is something that has to go into our understanding of what the Rydberg constant is. So if we were to make a definition based on hydrogen spectrum, it wouldn't be any different in principle than having it based on the spectrum of cesium, or for that matter, strontium. If we make it based on the Rydberg, then we don't have any way of realizing the definition nearly as well as the definitions that we have today. So that's why we're not, at least for the moment, going to redefine time in terms of a fundamental constant like the Rydberg. Now, is that always going to be true? I don't know. It might be that we get some breakthroughs either in technology or in theoretical understanding. It might be that by measuring the frequency separation of Rydberg levels in hydrogen, that we get rid of our dependence on understanding the nucleus. The trouble with the Rydberg levels is that they're very sensitive to electric and magnetic fields. So we have all kinds of additional problems. So there's no obvious answer right now. It looks like we're going to be stuck with having the unit of time be fixed relative to a particular atom. So I hope that at least answers the question a little bit.
Okay, so thank you, Professor Phillips, for answering this. John Freddy, he said he's from Colombia, but he's now in Brazil. And by the way, Juan Lima, that made the question about the candela, wrote in YouTube that he found your answer wonderful and he's very happy, and he always wanted to know about that, and now he's become knowing from maybe the person that knows the most about this fundamental constant. So he's thanking you very much. And we also, I should add that we have another graduate student, Rodrigo Ozella, that's doing the PhD with us. And he had essentially the same question about the candela and lumens and etc. But obviously, he said there's no need to do my question anymore because you have answered, right?
But you know, I'm afraid that people from the lighting industry and people who do measurements of light intensity might not be so happy with my answer.
Okay. So the next question is from Grigor's Hashwell. Grigor, do you want to make the question yourself, or do you want me to do it for you?
Yes, I think I can make by myself. So yeah, thanks. I want to thank Professor Phillips for a very nice talk. And I have more theoretical question or more fundamental. Because by fixing the value of the speed of light, do we completely deny the possibility that the speed of light can vary in space or maybe in time, like in some hypothetical cosmological scenarios? And the same about the Planck H constant, because by fixing H, do we really effectively declare that quantum mechanics is correct and it will be valid in this form forever?
Yeah. Okay. So no, I'm really happy that you asked that question because it really gets at some fundamental ideas. I would claim that the only constants for which it makes sense to ask, is this constant changing in time? The only such constants for which we can make such a question meaningful are constants that have no dimension. So for example, the fine structure constant or the ratio of the mass of the electron to the mass of the proton. These would be constants that have no dimensions, and therefore we could legitimately ask, do they change in time? Now let me expand on that idea a little bit, which will get at your question about, say, Planck's constant or the speed of light. right now, well, it's not right now. In general, in the SI, if we ask what is the fine structure constant, it's 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space, times E squared over H bar C. Now, as you implied, there have been experiments that show that on astrophysical timescales, maybe the fine structure constant is changing. Before the 20th of May of 2019, if the fine structure constant were changing, and we don't know that for sure because the observations are not clear enough yet, but at least it's not logically impossible. If the fine structure constant were changing before the 20th of May, we would have said this would have to be because some combination of E, the charge of the electron, and H were changing because C was defined and epsilon naught was defined. After the 20th of May of 2019, E and C and H are all defined and epsilon naught is no longer defined. So after the 20th of May, we would have said if the fine structure constant change, it must be because epsilon naught changes. Well, you can see how silly this is, that whether it's the electron charge or the Planck constant that changes, or whether it's the permittivity of space that changes, depends upon the date on which we ask the question. It just doesn't make any sense. So the only thing that makes sense to me is to say we will only talk about constants that have no dimensions. On the other hand, it's not impossible to imagine that you could measure the speed of light in different directions in space and see that that it changed depending upon the direction in which you were going. But then that would be because it was a ratio that you were measuring. As far as measuring the speed of light to be different in different regions of space, I think that has the same problem as the fine structure constant, because in general relativity, translations in space and translations in time, while not identical to each other, they're all translations in 4 space. And I think that in order for us to really make sense of what they mean, we should stick with dimensionless quantities. But it's a very deep question, and I don't believe everyone agrees with what I've just said.
Okay, thank you very much for your answer. Yes, it was very satisfactory.
Okay, so thank you, Grigors, for your question. Thank you, Professor Phillips, for your answer. Well, I mean, if you have questions, please manifest yourselves through the chat. We're approaching the end, right? So, but before that, let me mention that we had also the happy occasion of a visit of Professor Klaus von Klitzing to Federal University of Pará. So several years ago, he gave a talk, and where he mentioned, so it was like, how long is 1 meter, or if I remember correctly, and he spoke about also the Klitzing constant that you were talking about. And but before we come to an end, we have been talking, and as I mentioned in the introduction, you made a visit to Brazil, so in 2011, if I'm not mistaken. And you have visited Amazonia, and since we are in Amazonia, I would like very much, I mean, I'm sorry, it's not a question about physics, but I think it has a significance for us. You visited Amazonia, you came to Manaus and gave a public lecture in an outreach lecture in a public school in near the Negro shore. So you told me already this story, but I think, I mean, since we are recording this, and I think it would be really, really nice to have this registered, as said from you. I mean, and since also Vanderlei is here, I think this story deserves to be recorded and registered for all times.
Well, of course, the story is more Vanderlei's story than it is my story. Vanderlei is always trying to reach out to people to share the excitement of science, and as he does so often, Vanderlei was able to arrange something where we were able to visit this school. And my understanding is that the students who go to this school arrived by boat on the Rio Negro. Vanderlei, are you there? Do you want to say something about this school?
No, go ahead. You're doing very well.
Well, of course, it was Vanderlei who was giving the talk, because I might say a little bit and Vanderlei would translate it into Portuguese, but Vanderlei had a wonderful demonstration in which he gathered the children together to illustrate the idea of stimulated emission, about how a laser would work, and he had children run by groups of other children and pick them up and become part of the crowd of children who were running around. And he talked about stimulated emission, and I became a photon of stimulated emission. And it was great. But the thing that to me was most moving, and I think that Vanderlei can confirm this, that when we finished, and the students were just so enthusiastic, it was so wonderful to interact with them. One of the teachers told us that we had been the first people who had come from outside of this region to talk to their students about anything. And it was really very satisfying to know that we'd been able to provide some scientific enrichment to these students, but also a very sobering thought that we need to pay attention to the education of our students, not just the students who are in and near the big cities, but the students who are everywhere.
Okay, so thank you very much. I mean, this has been wonderful words, and these are more than necessary in the times we are living, Professor. So I would like to thank you very much. I must say that we have many compliments in the chats of the Google Meet and also in the YouTube. Fantastic talk, wonderful talk, and things like that. So, arriving at this point, I'll ask everybody again to turn on their microphones and to give a final round of applause. And thank you very much for this wonderful webinar that you have given for us. Thank you very much, Professor Phillips.